Hey, everybody. So most of what we were talking about with the last lecture was about observing the sky with the naked eye, about looking at, well, stars, but also planets and the moon, and trying to map the sky. Um, Given that when you look at the sky with the naked eye, you can see a lot, right? The human field of view is quite wide, and so you can see. Um, Lots and lots of objects all over the sky. And so we need some kind of way to map and organize all of that. This becomes really, really handy when you start observing the sky with the superior optics that you get from a telescope. Um, it's very hard to get your bearings when you're looking at the sky through a telescope. A telescope zooms in on a very small patch of sky, and if you don't know where you're looking, then what these stars are that you're looking at becomes really tricky. So, knowing how to map out the sky, either in altitude and azimuth or in right ascension and declination, um, becomes very powerful, because then if you know where you're looking with the naked eye, then you know where to point your telescope, and then you can consult star charts and your maps to confirm that you're looking in the right part of the sky and trying to find the object that you're trying to look at. So that's step one. Um, what else does a telescope do? Why do we use telescopes? Why are these instruments so handy um, for making astronomical observations? And how do they work such that we get meaning out of what we see? Right? If you're not really working that hard, then a telescope is just a big fancy camera, right? It takes pictures of the sky. Okay, cool. But if we're trying to discover something, if we're trying to learn about the universe, then we want to get valuable measurements. We want to get valuable information from the objects that we're looking at. And in order to get meaningful information, we need to know how a telescope works so that we know what it's telling us. So that's what we're going to talk about today. Um, Before we get to telescopes, though, we already use an optical instrument to observe the sky. We have eyes. Um, And your eye is an optical instrument, right? It collects light and it focuses that light to get a clear image in your eyeball, or hopefully clear, unless you need glasses like I do. But that's what an eye is, right? Your eye, just like a telescope, light goes in your eye, light enters through the pupil of your eye, and what happens after that? Well, what happens after the light goes in your pupil is that light passes through the lens in your eye, and just like the lens in a magnifying glass, that light gets focused. And if you have good eyesight, then that clear focused image that is focused, sharpened by the lens in your eye, that clear focused image shines on the back of your eyeball, where the back of your eyeball is lined in cells that absorb the light, and they create a nerve signal that gets carried by the optic nerve into your brain, and therefore your eye tells your brain what it sees. So your eye is basically it's the telescope that focuses the light, and it's the camera that records the image as a memory in your brain. And the human eye is really good, right? The human eye is a really useful tool for seeing what's around you, either on the ground or up in the sky. But the eye has some limitations, right? There's a reason why telescopes were invented, and that's because your eye is not perfect at looking at everything that you might want to see in the sky, right? Our eyes evolved to help us survive here on the land. They didn't evolve to help us do astronomy. Astronomy is a much more recent invention than eyes. So, what are the limitations of your unaided eye, and why do we invent telescopes to overcome those limitations? Well, Your eye, what happens? What did I say? The light goes in your pupil, it gets focused by the lens, and that focused image going in your eye shines onto the retina inside your eyeball. And your retina communicates to your brain about 25 times a second. So 25 times every second, your eye is constantly updating your brain. This is what I see. This is what I see now. This is what I see now. This is what I see now, right? Your eye is just constantly communicating to your brain the image that is getting absorbed by your retina. We have no ability to take a long exposure, right? Our eyes cannot soak up light over an extended period of time to make things look brighter, right? If we could point our eyes at an object and let our eyes absorb light for more time, then if we absorb more light, things would look faint objects would look brighter. And that's great for astronomy, because when we're talking about astronomy, almost everything is faint. We can't do that with our eyes. But you can do that with a camera. You can do that with a telescope. Our eyes have a fixed magnification, right, and a fixed field of view. Our eyes have no ability to zoom in and zoom out, right? We can't zoom in and make small things look bigger with a greater magnification, right? Our eyes have a magnification of 1. Right, that's the definition of a magnification of 1. A magnification of 1 means an object looks as big as it looks to the naked eye. We can't change that, but we can do that with a telescope. Our eyes have a small collecting area, meaning our eyes only collect light when that light enters our pupil, right? The light goes in your pupil and it gets focused by the lens onto the retina. So if we had larger eyeballs, right, if we had a larger collecting area, if we could collect more light per second, then faint objects would look brighter. That's why your pupils dilate at night. If you go out at night when it's dark, your pupils actually get bigger. Your pupils dilate to create a bigger hole that lets more light in, so that the dark world of the nighttime looks a little brighter, so you can see at night. During the daytime, right? During the daytime, it's bright out. You don't need as much light, and therefore your pupils contract and become smaller, so that your eyes are not overwhelmed by too much light going in every second. So our eyes have a slightly variable collecting area. Our pupils can get bigger or smaller depending on how bright the thing is we're looking at. But your pupils can't get, bigger than the size of your iris, right? The iris is the colored part of the eye. And so once your pupils have fully dilated, that's as big as they can get. That's as much collecting area as you can have. And our eyes also have a small wavelength coverage. What does that mean? There are, and we're going to go into this in another lecture in a few days, but there are lots of different wavelengths of light, right? There's more light in nature than the stuff that our eyes can see, right? Our eyes can see wavelengths, from red, orange, yellow, green, blue, violet, right? Our eyes can see visible light. Our eyes can see colors, but our eyes can only see the wavelengths and the colors that our eyes are sensitive to, that the cells in your eye respond to. There are all these other kinds of light: infrared light, ultraviolet light, X-rays, radio waves. There are all these different wavelengths of light that we've got names for, infrared, ultraviolet, and all that. It's light, but it's not light that our eyes respond to. It is light that is invisible to our eyes. And so if we wanted to see the light, if we wanted to see the ultraviolet light or the infrared light or the radio waves given off by some object in the universe, we would need to design an instrument that is sensitive to those wavelengths. We would need to design a telescope and a camera that does respond to infrared light or ultraviolet light, because our eyes don't do that. So our eyes are great. they've kept us alive for a few million years, right? So all well and good. Um, but if you want to look at faint objects really far away out there in the universe, which is sort of a good working definition of what astronomy is, um, we need some better devices, right? And that's where lenses, mirrors, and telescopes come in, right? Lens making really started getting good around the early 1600s because what is a lens, right? A lens, and I'll flip back here in a second, but a lens is what? A lens is a piece of glass that is polished and curved to just the right shape that it focuses light, that it takes rays of light and focuses them to a focal point. And that takes work. It's not trivially easy to make a lens. You've got to make glass. Then that glass has to be like really well made. It's got to be nice and transparent and flawless and crystal clear. And it took people a long time to figure out how to do that. And so the first people to really crack it were the Dutch. The Dutch were the first people to make really high quality lenses in the early 1600s. And originally they invented lenses to make things like spectacles, right? Eyeglasses, magnifying glasses, that kind of thing. But then, pretty quickly they realized, oh, you could combine sets of lenses to that are even more powerful to create things like telescopes and microscopes. Galileo probably gets, well, he did a lot, but maybe he gets too much credit. Maybe he's too famous for his own good. But Galileo, I think there's a common misconception that Galileo invented the telescope. He didn't, right? It was those Dutch lens makers that invented telescopes. But Galileo was the first astronomer to buy a telescope, take it apart, see how it works, and then he put it back together to be more useful for astronomical applications. And so Galileo didn't invent the telescope, but he sort of improved on the design to do things like looking at the moon, the planets, the stars, galaxies, that kind of stuff. What is a telescope? What does a telescope do? Well, a telescope is basically a light bucket. A telescope is designed to collect light the way a bucket collects rainwater, right? Whether you do it with lenses or mirrors, a telescope, the basic job of a telescope is just collect light, bend that light and bend that light so that the rays of light come to a clear focus. And then once that light is focused, shine it somewhere useful. Shine that clear focused image into your eye or into your camera, something, where you want it, where you want to see the image. The very first telescopes were all refractors. They were all lens-based. And so a refracting telescope works like this, right? You need two lenses. The objective, the lens out front here is called the objective because it's the thing you point at the object, the astronomical object. The objective lens is basically the thing that collects the light. So you point your telescope, the light from whatever star you're looking at shines through the objective lens, it comes to a focus. So here's the focal point, right? The focal point is where the rays of light come to a focus. And if that's all you had, if all you had was one lens, then if all you had was one objective lens, it would basically be like looking at the world through a magnifying glass, right? If you've ever tried looking through a magnifying glass, it works to a limited extent, right? Looking through a magnifying glass is the image gets distorted, and it's limited, right? Because if all you have is one lens, you're only going to get one magnification. So to make it better, to make this telescope clearer, to make the image less distorted and clearer and more focused, and also to have a more versatile instrument, you've put on a second lens, the eyepiece. So that light, the light comes from the objective lens, it comes into focus, then it goes out of focus and it shines into the eyepiece, and the eyepiece does the final bending. It does the final tweaking, clarifying, focusing, so that what comes out of the eyepiece is a clear, focused, less distorted image shining into your eye. And then all you got to do is put your eye up to the eyepiece, and that clear image should be shining straight into your eye so that it's easy and clear for you to see. Like the homework goes over, two of the fundamental properties, two of the really important main properties of a telescope are the focal lengths, right? The focal length is just the length from the lens to the focal point. So FO here is the focal length of the objective. FE is the focal length of the eyepiece. And those two focal lengths determine what kind of an image you're going to get from that combination of lenses. So the focal lengths of the objective and the eyepiece are two really important things to know about a telescope in order to understand why you're getting the image that you're getting. After 150, almost 200 years, no, just about 100 years. After about 100 years, people realized you could do the same thing, but with mirrors instead of lenses. And so after a while, by the end of the 1600s, people invented reflecting telescopes, where instead of an objective lens collecting the light, you have this primary mirror, and the primary mirror is concave. It's curved so that the light comes in the telescope, the starlight comes in the telescope, it bounces off this curved mirror, and it comes to a focus. And again, if you put your eye right there at the prime focus, you would get a focused, magnified image coming off that primary mirror, but again, it's distorted, it's not quite user-friendly. So what you do is you stick a secondary mirror in the middle of the telescope, and the secondary mirror's job is just to bounce that light somewhere convenient, like off to the side here, where that light, again, shines through an eyepiece. The eyepiece does the final tweaking and focusing, just like in the refractor, and then the image shines out of the eyepiece into your eye. Fundamentally, a telescope does the same thing. Whether you're using lenses or mirrors, the telescope collects the light, bends the light to a focus, and then shines that focused image somewhere convenient. How you do that, the exact details are just that. They're details. Right? Every telescope in the world looks a little different. Every telescope in the world is designed slightly differently because you want to have the right tool for the right job. And so most of the time these days, all big modern telescopes are reflectors. They're mirror based because, well, there's a whole bunch of reasons why reflectors are fundamentally superior. Right? Whenever light shines through a lens, you're going to lose some of that light. It's going to get absorbed by the lens. And if you're looking at some dim object, you can't afford to lose light because the object's already dim. Every photon is precious at that point, right? You can focus light better through a mirror than you can through a lens because lenses tend to refract light and disperse it into a rainbow. And so that when you spread the light out into the rainbow, you get weird distortion effects that blurry the image, and that's not easy. That just makes your life harder. For that matter, what is a lens? Right? A lens is a solid slab of glass that you've got to curve on both sides. You've got to polish that lens to the right shape on both sides so that if you want to make a big world-class telescope, having a giant objective lens on the top of that telescope, if you want to make a refractor telescope, that objective lens is going to be big, heavy, expensive. Right? Making a solid slab of glass that is perfectly transparent and then polishing it perfectly on both sides so that it focuses the light perfectly, it becomes a very expensive proposition. The last time somebody made a really big refractor was about 100 years ago. It was a little over 100 years ago. And the world's biggest refractor it's called the Yerkes telescope in Wisconsin. It's massive. It was crazy expensive to make, and after that everybody kind of went, you know what, this isn't worth it, right? If you have a reflector, right, a mirror is what? A mirror is just a thin sheet of metal that is polished to just the right shape, right? You only need to curve one side of a mirror. Who cares what the side? Who cares what shape the backside of a mirror is in? The backside's not doing any of the work, right? So, yeah, these days, all the big modern telescopes are mirror based because you can make them bigger, you can make them lighter because you don't need a solid slab of glass. You just need a thin, curved, shiny surface to focus the light. So you can make them bigger, you can make them lighter, you can make them cheaper, and they focus the image better. So basically, if you're a professional astronomer and you want to spend millions or $1 billion making the biggest telescope in the world, it's going to be a reflector. So that's what we've been doing for decades now. Right? Notice I keep talking about how the size of the mirror, the size of the lens matters, because that's the other important thing. The two important characteristics to know about a telescope are the focal lengths and the diameter. Every telescope in the world is defined in terms of the diameter of the objective or the primary mirror, because the bigger your primary mirror, or the bigger your objective lens, the bigger your light bucket is. Right? And if you've got a bigger light bucket, you can collect more light per second, you can make faint objects look brighter, you can see deeper into the universe. So the bigger the diameter, the more you can see into space by making faint objects that are far away look bright enough to be visible. So this is a replica of Isaac Newton's little reflector telescope that he used when he was doing some observations at the beginning of his career, or actually throughout his career. This is a 3.5-inch diameter. So again, when you talk about a telescope and you give a length, that's not the length of the telescope, right? The telescope is not 3.5 inches long. The telescope, the mirror back here, the primary mirror back here, is 3.5 inches in diameter. That's the important thing. This is a couple of pictures of the big Mayall 4-meter telescope up on Kitt Peak. Right? The Mayall is a 4-meter telescope, meaning 4 meters long? No. The length of the telescope tube doesn't really matter. That's just details of engineering. The important thing is the diameter of the mirror. So the primary mirror here is 4 meters. So this is pretty big, right? 4 meters is 12 feet, over 12 feet in diameter, pretty darn big. And this is, unless my memory's failing, I think this is the biggest telescope up on Kitt Peak, although there are a lot of other telescopes on Kitt Peak. This is one of the new big instruments, and I think the biggest in Arizona these days. This is the Large Binocular Telescope up on Mount Graham, a couple of hours southeast of here, outside of Safford. This telescope has two 8.4-meter mirrors. So it's a twin 8-meter telescopes. Each of those mirrors is 8.4 meters in diameter. Let me try to get a sense of scale, right? This is a giant thing. Like, this is literally awesome. Being inside of this observatory is just, everything is huge. And so, like, this building is big, and I'm thinking, like, okay, let me, okay, right there, those rectangles right there are the mirrors in, I think those are the mirrors in the cafeteria. Um, so, like, look at the big window in your living room, let's say, right? The big mirror, if you have a big nice window in your living room or something, that's the size of it right there. That little window there is the size of, like, the big window in my living room anyway. Um, so this is a several stories tall. Um, this is an artist's rendering of what will become the biggest telescope in the world when it's finished being constructed, which hopefully should be around 2027. This is a rendering of the 30-meter telescope, right? So this is going to be this telescope is going to be up on the top of Mauna Kea in Hawaii. The one mirror is going to be 30 meters in diameter. So that's about 100 feet in diameter. And if you wanted to make one mirror 100 feet in diameter, good luck. It would be a massive job, and there's no foundry in the world that can make a mirror that big and that carefully. Right? You make a sheet of glass 100 feet long. Okay, that's doable. But make a sheet of glass that is perfectly shaped to focus the light. To my knowledge, there isn't a foundry big enough in the world. So instead of making one mirror that size, they're basically going to make 492 small mirrors, and then they're going to tile those mirrors together to create a mosaic. And once you tile all those mirrors together, the overall shape will bend the light and focus the light perfectly to create a clear and focused image. So this thing is going to be absolutely massive. And they've been working on building it for a couple of years now. It's going to take several years more for all the equipment to get installed and tested, and for the science mission to begin, which I think on the current schedule is about 2027. So, keep an eye out for this. After the semester is over, keep an eye out for this in the news, because when this thing finally opens, it is going to be awesome. Why did I say that the focal lengths are important in the telescope? Because the focal lengths of the objective and the eyepiece are what determine the magnification that you get. The magnification on an image it's just the ratio of the focal length of the objective to the focal length of the eyepiece. All right? So take the focal length of the objective divided by the focal length of the eyepiece. That'll tell you the magnification that you expect to get from that image. So let's just say, for example, all right, if you built a telescope where the objective has a focal length of 1250 millimeters and the eyepiece has a focal length of 25 millimeters, what magnification will you get from that? I'll let you grab your calculator. Yeah. So 50 times. Right? So with that combination of lenses, your image is going to have a magnification of 50. Which means what? It means that every image that you take with those two lenses, every image that you take with that telescope will look 50 times bigger than it looks to the naked eye. Yeah. So, what do you think? Right? Think about the relationships here. All right. Without reaching for your calculator, which of these is going to have the greatest magnification? If they all have the same objective, and if the only difference is the eyepiece, then the highest magnification will come from the shortest focal length eyepiece. So A it is. Which of these will give you the greatest magnification? Yeah, C it is, right? A long focal length objective and a short focal length eyepiece, that's what will give you the greatest magnification. So what do you think about this? I kind of just gave it away, didn't I? Right? The greatest magnification will come from the longest focal length objective and the shortest focal length eyepiece. So the answer is D. Yeah, D it is. Okay, so the focal lengths are important because they give you the magnification. The magnification from the image will affect one other thing, and that is what angle on the sky you can see, right? Because when you look at things in the sky, you can't just look at something and say, oh yeah, that looks an inch long or an inch wide or something like that, because you're not seeing the linear size of something, right? You're seeing the angle. If something gets farther and farther away from you, is it going to look bigger or smaller? I don't know, if something's farther away from you, it's going to look smaller. So when you're measuring positions, sizes, the size things appear on the sky, you're measuring the angle. The angle between the left side, your telescope or your eye, and the right side. And typically when in most math classes, when we measure angles, we usually measure that in either degrees or in radians. For our purposes in astronomy, a radian is way too big. 1 radian is a really huge angle, way too big for us. In fact, 1 degree is too big in astronomy. Think about this. How big is 1 degree? All right, it's a useful. Well, I almost called it a rule of thumb, but it really is a rule of thumb. Look at this for yourself. Okay, hold your arm out at arm's length and stick your thumb up. All right, look at your thumb when you hold it at arm's length. All right, it's one of those great symmetries of the human body that when you hold your thumb at arm's length, all of our thumbs look the same size. They look 1 degree wide. Meaning what? It means that the angle from the left side of your thumb to your eye to the right side of your thumb is 1 degree. So 1 degree, even when you hold it at arm's length, right? One thumb is big. It's about twice as big as the sun and the moon, right? The sun and the moon, right, 2 of the biggest things in the sky, are only half a degree wide. So even like the biggest stuff in the sky, like the sun and the moon, you're not going to measure their size in degrees because even a degree is too big. So when we measure angles in the sky, we tend to measure those angles with smaller units. So what we do is you take 1 degree and you break it up into 60 what are called arc minutes. So there's 60 arc minutes in a degree. And so you could say, well, how big is the full moon? The full moon is 30 arc minutes wide. Okay, all right, so 30 arc minutes, all right, not too bad, right? The numbers are manageable. But saying, well, 30 arc minutes, 31 arc minutes, something like that, that's usually a lot more user-friendly than measuring fractions of a degree. When you start talking about the size of really small things, small galaxies, small nebula that are really far away, even arc minutes become too big. And so if you're measuring really small things where even an arc minute is too big, then we take 1 arc minute and divide it up into 60 arc seconds. So measuring these angles is a lot like time, right? It's a lot like hours, minutes, and seconds, where it's 60 arc seconds in an arc minute and 60 arc minutes in a degree. Just like hours, minutes, and seconds, right? So that's how you can remember it. Okay. Why am I going over all this? Well, because here are two images of the same object, right? These are two images from two different telescopes of the Eagle Nebula. And so you'll notice, all right, this part here, right, this is the whole Eagle Nebula. This picture here is just a zoomed in magnification on these central pillars of gas here in the middle of the Eagle Nebula. So these are both two pictures of the same thing, but this image is 7 arc minutes wide. This image is only 1 arc minute wide. Your field of view, right? The field of view is a measure of how wide your image is. What angle on the sky is subtended by the image that you're taking in your telescope. So on that picture on the left, right? That left picture, what I'm telling you is the angle from the left side of the picture to your eye, or to the telescope, to the right side of the image, is that angle is 7 arc minutes wide. The image on the right is more zoomed in, so you're only capturing 1 arc minute wide in the middle there. So what do you think? Which of these images has the wider field of view? Well, image A is, right? Because this image is 7 arc minutes, and image B is only 1 arc minute wide. The object has not changed size, right? We haven't done anything to the nebula itself. The nebula is just a cloud of gas floating out there in the galaxy. But what we've done is we've zoomed in or zoomed out to get a wider image or a narrower image. Which of these images has the higher magnification? Higher magnification means small things look bigger. So B has the higher magnification. That's the trade-off. That's why I say every telescope in the world is designed a little bit differently, because you want to have the right tool for the right job. Sometimes you want a wider field of view and therefore lower magnification, because you want to capture the whole nebula in your image. Sometimes you want to zoom in with a higher magnification and a narrower field of view, because you want to take these small details, you want to take the small objects and make them look bigger so that you can see smaller objects captured in your field of view. Pick the right tool for the right job, depending on what your job is. And therefore, if you know what kind of image you want to take, if you know the width and the magnification that you desire, well, then you would pick the focal length of the objective and the focal length of the eyepiece to get you the magnification and the field of view that you want. All right. The other important thing to know about a telescope is the diameter of the mirror. Because with a larger mirror, you have a larger light gathering power. You have a larger collecting area. And if you have a larger light collecting area, you can capture more light every second. And if you're able to capture more light, if you're able to collect more light every second, then faint objects look brighter and you can see deeper into space. So if you have a 1 meter mirror and a 10 meter mirror, how much more area does the larger mirror have? Well, that 10 meter mirror has 10 times the diameter of the 1 meter mirror. If it has 10 times the diameter, how much more area does it have? Well, the area of a circle depends on the diameter squared, right? The area of a circle depends on the diameter squared, or the radius squared. And so if you have 10 times the diameter, the 10 meter telescope, the 10 meter mirror has 100 times 10 squared. It has 100 times the area. And so that 10 meter mirror is going to be able to get 100 times more light every second. You're going to make faint objects look 100 times brighter every second. And so, for example, here's two images of the Andromeda Galaxy. These two images are the same magnification, the same field of view. The only difference is one is taken with a larger mirror. With a small mirror, all you're going to be able to see are the really bright parts. But if you have a larger mirror and you're able to take those faint details and make them look visibly bright, then all of a sudden you can see all the little faint details on the arms of this galaxy. You can see all these little dwarf galaxies orbiting around there. Now they look brighter. Right? So having a bigger mirror is almost always better. I mean, sure, a bigger mirror is more expensive, but as you make bigger and bigger mirrors, faint objects, which is to say most of the universe, looks brighter and more visible, and you can see more details and you can learn more about how the universe works by being able to see the fainter details. One more thing. When you have a bigger mirror, you also have a clearer image. You can see smaller angular details. This is a little hard. This is a little more complicated. So let's think about this for a second. All right. When you see something really far away, when you look at something really far away, that object looks blurrier because it's not that the object has gotten bigger or smaller, but it looks smaller. So let's imagine that you're standing there on the side of the road and you're looking at a car coming toward you. When that car first comes over the horizon driving toward you, you might not be able to resolve. You might not be able to see both headlights. You just see one light source coming toward you. And as that car drives toward you, that car gets brighter, obviously, but eventually that one light source starts to elongate, and eventually it becomes two clearly visible headlights as the car drives past you. When that car is way on the horizon, you're probably not going to be able to see two individual light sources. It's just going to look like one blob of light. Why? Because the angle between the two headlights is too small. Every optical device, your eye or a telescope, every optical device has a limit to how small of a detail it can resolve, how small of a detail you can pick out as two individual details. But as that car drives toward you, the angle between the left headlight, your eye, and the right headlight, that angle gets bigger and bigger and bigger until that angle becomes large enough that you can resolve that those are two separate headlights. So usually the equation is written like this one here, where you say, okay, alpha here. Alpha is the smallest angle that you can still resolve. Right? Alpha is the size of the smallest detail that your telescope can see. Any smaller detail will just be blurry and you won't be able to make it out. Any larger detail is clearly visible, but alpha is basically the cutoff, where this is the smallest detail that you can resolve. And that alpha, that angle, that minimum resolvable angle, is 12.5 arc seconds divided by the diameter of the mirror in centimeters. So if you have a larger diameter, If your telescope has a larger diameter objective, what happens to the alpha? As diameter increases, alpha decreases. And that's a good thing, because a smaller alpha means you can clearly see smaller and smaller details. This might be a little counterintuitive, right? Usually we're used to thinking of like, the bigger number is better. Well, in this case, a smaller alpha means it's better because you can see smaller details. So for instance, okay, here's a binary, here's two pictures of the same binary star, right? If you've got two stars that are right next to each other on the sky, you might not, if you've got too small of a telescope, or if you're looking at that binary system with the naked eye, you might not be able to see that it's two stars. It'll just look like one star. But then if you switch to a bigger telescope, if you switch to a telescope that has a larger mirror, you'll be able to resolve smaller details, like the fact that that's not one star, that's two stars. So this is where it seems a little bit counterintuitive, right? Having a larger resolution means you can only see large details and not small details. Having a smaller angular resolution means you can pick out smaller and smaller details, and you can see the world, or you can see the universe more clearly. Your image is clearer. So again, here's 4 pictures of the Andromeda Galaxy. Which of them has the largest angular resolution? Well, having a large resolution means you can only see large details and not the small details. So which of these only lets you see the large details? A, it is. Which of these images was taken with the largest diameter objective mirror? Well, having a larger objective mirror means that you're able to see smaller and smaller details. So the largest diameter must give you the most clear, most detailed image, which is D. Yeah. Right? So this is why astronomers and the engineers are always trying to make bigger and bigger telescopes. The 30-meter telescope is going to be awesome because it's going to be the biggest telescope in the world. Why are we putting all this time and energy into making the biggest telescope in the world? Because a big mirror means you have a larger light collecting area, meaning you can take faint objects at the edge of the universe and see them more clearly, where you can see them brighter. They'll look brighter. But also, the win-win is that with a bigger mirror, you can also see the universe more clearly. You can see smaller and smaller details that otherwise are just too blurry to make out. We need to understand how a telescope works in order to say, well, why am I getting this picture versus that picture, right? Which of these pictures is more realistic? Which one is giving us a better view of the universe? Well, if you don't know how a telescope works, then that's not really an answerable question. But if you know that the angular resolution shows you more detail, then you could say, oh, more detail means we're getting a clearer view of what the universe really looks like. So this must be the better picture for telling us what is really going on in Andromeda. All right. So I hope that helps with the telescope homework and clarifies some of these issues, because these are important for figuring out other properties of stars that we're going to start on in the next lecture. So go ahead and finish up the telescope homework, and I'll see you in the next, or you'll hear me in the next lecture. All right. Have a good one, everybody.